So looking at in-class momentum, let's look at question number 2. Question number 2 on that in-class momentum says, what is the magnitude of the average force experienced by a 0.25 kilogram block that was moving at 5 meters per second before it collided with a wall and it stopped in 0.3 seconds? So what is the magnitude of the average force? What I'm asking you to solve for is the force in that equation right there. What is the magnitude, how big of the force? So a couple substitutions that I kind of done a few times is this is the equation we're going to use. Now this is not maybe the most user-friendly equation directly, but if we do a quick substitution, we say, well, delta P is P2 minus P1, right, P2. So instead of writing it as F times delta P is equal to F times delta T, we could write P2 minus P1 is equal to F times delta T. And then we could do a couple other substitutions and we could say, well, how do we find P2? Well, P2 is nothing more than M times V2, P2. And P1 is M times V1 for P1, which then we can say is the same as delta P, which is that equation that I had on the board the other day that looks something like that. That's just a couple substitutions along the way. So if I were to say delta P is really P2 minus P1, I'm just going to do it again over here. Probably not necessary, but I'm going to. So delta P is P2 minus P1, and instead of saying P2, I can say MV2 minus MV1 is equal to F times delta T. So P2 minus P1 is delta P. M times V2 is P2. M times V1 is P1. That's where that is. So now we look at through the problem, and it says, what is the magnitude of the average force solving for F? 0.25 kilogram block, there's your mass. It was moving at 5 meters per second before it collided with a wall and stopped. So what is 5 meters per second? Is that your V1 or your V2? 1. And how fast is, what's your V2? What's V2? We just said V1 was 5. What's V2?
0.
Because it stopped, right? So that means that term is 0. M times V, if V is 0, then P is going to be 0. So 0 minus the mass of 0.25 times 5 is equal to F times the time of impact, and that time of impact is 0. So 0 minus, so negative 1.25 is equal to F times 0.3. Divide both sides by 0.3. And we get a value of 4.17. Negative 4.17. Okay, average force, simply asking you to solve for that. Now, the next problem number 3 on that worksheet on in-class momentum, deals with that fourth equation that I introduced before I hit record on the video. So that fourth equation that I wrote on the board is called the conservation of momentum. It means the sum of all my momentum before the collision or interaction is going to be equal to the sum of all my momentum after the collision or interaction. So if we take a look at this third one, this is a two-object interaction. 80 kilogram astronaut is floating in space repairing a satellite. The repair is complete, so she radios the shuttle and tells them to initiate the startup sequence to return to Earth. When she pulls on the tether, it was somehow cut and she is unable to pull herself back in. Armed with only a 1 kilogram space wrench, she throws it as hard as she can, 5 meters per second, hoping that she will drift back to the shuttle in time. Which direction will she need to throw the wrench, and how fast will she move towards the shuttle after she throws the wrench? Okay? a little thing, something to talk about. In space, there's no air. So here on Earth, if I wave my arms through the air, I can move it, right? I'm hot, I can move air, I can cause a fan. If I were in a pool, I can go like this, it's called swimming, and I can move through the water because I'm pushing against it. In space, there's nothing to push against, right? So if you were an astronaut floating in space and you go like this, you're not going anywhere, okay? So oftentimes they will attach themselves with a rope, fancy word, tether, and the idea is when they're done they can just pull themselves back in because otherwise they don't go anywhere. You sometimes see in movies, and actual astronauts too, there's this big suit that or backpack, essentially, that they can attach to their backpack, and there's some letters, I think, that it talks about. But all it is really like a compressed air jetpack, and then they can maneuver through space by squirting little bits of compressed air that propels them forward and backwards or side to side. Okay? So, assuming they don't have that on, they use ropes. And if they don't have that, well, then they can potentially not get back to the space shuttle. So, what we have is this astronaut who's stuck in space, and I'm going to draw a beautiful picture for number 3. And here is our astronaut holding a wrench, because there's 2 objects. And obviously this is the astronaut because the astronaut is bigger than a wrench, clearly. So we start with an astronaut and a wrench. Now what conservation of momentum says is all my momentum that I start with before has to equal all my momentum afterwards. So I go through and I draw like before and after pictures. So this is my before picture. We're going to have to calculate some momentums, and momentums is mass times velocity. So I really have 2 objects that are stuck together as one. So when I talk about the momentum of this object, I need to know the mass of this object, which I just simply call the mass of object AB. Right? It's A and B stuck together, so I call it object AB. And I'm going to need to know the velocity of object AB before she throws the wrench. If I know the mass, and if I know the velocity, I can calculate the momentum. And if I know all of the momentums of all of the objects before the interaction, I can sum up all my momentums before. So, let's talk about this really quick. This is probably the one and only time I'll write it like this, but in order to determine the mass of object AB, I simply take the mass of object A, and I add it to the mass of object B, so 81 kilograms. I'll probably never do that addition on the board again for you, but they're together as one. So 81. How fast are the astronaut and the wrench together as one, moving before she throws the wrench? 0. She's floating in space. Now you could say, but, oh gosh, Mr. Davies, the astronaut is actually in orbit around the Earth, so they're not really moving 0. Aren't they really moving at like 20,000 some miles per hour? And I think the answer is yeah, it's something like that. But relative to the space shuttle, she's not moving. So it's this thing called relative velocity, so let's not worry about that. So she has no momentum beforehand. And if the space shuttle is maybe like behind me and over my shoulder, if she takes an object and she throws the object, some direction, okay? That object, that wrench, is going to have some momentum. And what that 4th equation says is that if I add up all my momentum before, it has to equal the sum of all my momentums afterwards. So her and the wrench collectively start with 0 momentum. She's not moving, the wrench isn't moving, they're floating in space, not moving. If she wants to go towards her spaceship, which we could say she's object A, and she wants to go this way, because I said it was over my shoulder, she has to acquire some momentum in this direction. She has to have momentum in this direction, because momentum in this direction means she's moving with a velocity in that direction. her momentum plus the momentum of the wrench have to add up to the momentum that we started with, which in this case is 0. So if she wants to go that way, which way does she need to throw the wrench? That way, right? She has to give the wrench some momentum by throwing it in that direction. The harder she throws this thing, the more momentum the wrench will have, and the more momentum she's going to have in the opposite direction because they have to add up to what this does. We'll talk about that in a second. So, in order for her to go this way, she has to throw the wrench that way. Okay? I guess the other option is she could throw the wrench at the space shuttle and hope that they hear it hit before they leave. Or, if I'm not going to make it back, I'm going to crack the windshield and none of us are making it back. That'd be kind of a cruel thing. And probably wouldn't, a wrench probably wouldn't do it, by the way. They kind of build those things pretty tough. But in order for her to drift backwards, she's got to throw the opposite direction. So we end up with 2 objects. So our momentum afterwards is 2 objects. We need 2 objects. We have 2 momentums. And how we find those momentums is mass of object A times the velocity of object A after the collision. And how do we find the momentum of object B? We need the mass of B and the velocity of B afterwards. And by doing it like this, I think it really helps set up that equation. So, some information was given in the problem. The mass of the astronaut was 80 kilograms. The mass of the wrench was 1 kilogram. And she throws it with 5 meters per second for velocity. Now, if, according to my picture, is that a positive 5 or a negative 5? For my picture, is this in the positive or negative direction? As a positive direction, okay? Which means she is going to have a negative. To be determined, we're going to calculate that, but it should end up being a negative number. So that's kind of the setup process for this. Now to actually use the equation, that 4th equation, conservation of momentum says, the sum of all my momentum before, sum of momentum before the interaction, is equal to the sum of all my momentum, the momentums after the interaction. I start with one object. So I have to add up all the objects, there's only one, so I need to calculate the momentum of object AB, that one object, before, at location 1, she throws a wrench. So this is PAB1. All my momentums before, there's only one object, and it's object AB, is sigma P1. After she throws the wrench, we end up with 2 objects. So I have to have 2 momentums. I have the momentum of object A, and I have the momentum of object B that I'm going to add, that's what sigma means, together. And I'm going to put a 2 next to them because it's after the collision or after the interaction. So PAB1 equals PA2 plus PB2. This is the original equation. This is the generic equation that we built to fit the situation. There's 4 different situations that we're going to build. This is a special one. This is a particular one, just for the record, that we call a recoil collision. This is a recoil collision or interaction, it's not really a collision, that we can go through. Now, P is momentum, and momentum is mass times velocity. So in order to calculate PAB1, we take the mass of AB times the velocity of AB at location 1 to give us PAB1. So that's why I draw like this, because then all we have to do is go this times this gives us this, and we can kind of work it. So I'm going to write it out. MAB times VAB1 is how we are going to calculate PAB1, because momentum is mass times velocity. So if we're talking about the momentum of object AB, we need the mass of AB, we need the velocity of AB before she throws the wrench. Equals the momentum of object A at location 2. So momentum is mass times velocity, so it's the mass of object A times the velocity of object A after the collision or interaction, plus the momentum of object B, which is the mass of object B, times the velocity of object B times the velocity at location. because this velocity is 0, we start with no momentum. She starts with no momentum because she has no velocity. So that's going to equal 0. So 0 is equal to 80 VA2. That's what we're trying to solve for. That's where I put my question mark. Plus the mass of object B was 1 times the velocity was a positive 5. 0 equals 80 VA2 plus 5. Cannot combine unlike terms. So I can't say 85 because this is a VA and this one doesn't. So I have to subtract 5 from both sides. And I end up with negative 5 equal to 80 VA2. Divide both sides by 80, and our VA2 is equal to negative, tells me the direction, 0.0625 meters per second. So she's going to drift towards the space shuttle at about 6 centimeters a second. Not super fast, but she's going in the right direction. Now let's say that you just pretend for a second that this was you in a pool. Would you continue to move at a constant velocity of 0.0625 meters per second, or would you eventually come to a stop in a pool of water? Come to a stop. Good. Good. Whoever that was. Why? Because there's water and it has friction in it. So it's going to slow you down. However, she's not in water. She's in space. Does she need to keep throwing stuff to keep moving, or is she just going to drift at a constant speed once she starts moving? Constant speed. It's kind of like the Mars rovers. Like once they're pointing in the right direction towards Mars, they can turn off their rockets and kind of just drift and coast, and they're going to get there because they're going in a straight line. And that air isn't going to slow them down or change their course. Okay, not super fast, but she's going to make it. Well, she's going to move towards it. That question, the part I crossed off was like, the startup sequence takes 5 minutes. Will she make it in time? That would actually become a Fab 5 problem. But she'd be moving at a constant velocity, so we're not going to mess with that. So this type of interaction is referred to as a recoil interaction. So recoil is any time objects start together and end apart. Recoil, when I think of recoil, I think of guns, because we talk about a recoil of when you shoot a gun or fire a gun. Yeah. I think she did. She was how far away? 5 minutes, 15 meters. She's moving at a constant velocity. Took her 240 seconds. Oh, oops, 60. 4 minutes. Minute to spare. She even maybe got to put a seatbelt on before they left. Yes. Thank you for your concern. I appreciate that. So recoil, I think of guns in terms of recoil. And it's the same type of interaction. You start with a bullet in a gun. There's a firing pin that ignites powder, rapidly expanding gas. The bullet goes pew, flying out that way, and you, the gun, the bullet, whatever, get kicked back, right? There's recoil. So that's a great example. Spacewalks, they use suits for recoil. They just squirt compressed air. They throw compressed air out. You see this in movies sometimes. They do it in space. Like in The Martian, he poked a hole in his spacesuit, and then that compressed air from his spacesuit, he was able to propel himself. It's kind of the same idea, but instead of throwing a wrench, he used compressed air. They use it to change directions in rockets. You also, the movie Gravity, I think it was, she used like a fire extinguisher. The same idea, compressed air would compress something, probably a CO2 one. She could use it as like compressor, I guess you could say. Okay. Jet skis, that's essentially what a jet ski is too. You take, it's not gas, but you take water, you compress it and you push it out the back, which causes your jet ski to move forward. There was a thing I read about a couple years ago called a flyboard. It's basically they take a jet ski, they take the propulsion unit of a jet ski, and they hook a hose up to basically the nozzle of the jet ski, and then they have water squirt out the bottom, and then based upon how she steers that water, and she's got a handheld controller of some sort, it looks like, to control the throttle. It's kind of like, it's Iron Man, right? It's Iron Man, but on water. A couple years ago, I feel like someone said that there was a place up in like Minocqua, Tomahawk or something that rented those, but I don't remember. Anybody ever see these in real life? Yeah, where?
My cabin. They rented one.
You guys did?
No,
Oh.
one on our lake.
Okay. Okay. And were they this good? Or did they fall a lot? Yeah. I'm guessing it's probably, this is apparently the world champion. I didn't know there was world champions of it. But the idea was, now a different video I saw, they had like hand nozzles too. And the hand nozzles could then like direct them, kind of steer them and cause them to spin and rotate. But, so apparently it's a thing that you could rent if you want. I don't know where you rent something like that, but apparently you can. So this sheet, half sheet, there's 4 calculations that I'm going to ask you to do. I have the answers sitting on that table right there. These are using equations 1, 2, and 3 on the board, not the 4th equation that I just introduced today. But it's looking at those. So the combination of these 4 calculations and the worksheet that I gave you the other day, I don't remember when I gave it, do seatbelts work better than your face in the windshield? There's a front and back to that. Once you finish that half sheet, finish this up. I don't have your Canvas page built yet, sorry. Terrible person. So hang on to this. I'd like it done by Monday. I'd like this done by Monday. But I don't have any place for you to give it to me, so just hang on to it and we'll talk about how you're going to give it to me on Monday. A couple things on this sheet. When you get to number 3, the side that says practice problems, it talks about a lump of clay, part A. That's either a free fall Fab 5 problem or it's an ME1 equals ME2 problem. Do not use 0.2 as the time that it takes to fall 15 meters. That is not the amount of time it takes to fall 15 meters. That is the amount of time it takes to the impact. That's that time right there. Okay, so that's part A. Part B, if you solve for F in that 3rd equation, you're going to be about 2 newtons short. And it says hint, don't forget about F of G. Because the clay has some mass times 9.8 is going to give you the force of gravity, a little bit of weight, and that's going to make up for that difference. So, those are some things that people are kind of getting stuck on. So let me know what I can do to help you along the way. Half sheet answers, check yourself, are right there, followed by this worksheet, do seatbelts work better than your face in the windshield. You might need a copy of this. I don't even remember what day this was. I don't remember if this was yesterday or the day before. Yesterday. 3. You can ignore the video. Ignore the video, by the way. Okay, so once you're done,